you think, what's next? She really listened to the instruction very carefully and does the thing that she was told to do, which is really, something like virtual, right? Because you want to have a student who does the things based on, the plan. So in the last year or so, she's been really working on something that's a continuation of a project that I started almost like 2 years ago, which is related, as you will see in a second, related to this, solar business. And the work she's been doing really is fundamentally important because, again, I'm sure she's going to mention the importance of this. But for me, I feel like, this person is really caring. She often comes to my office and asks me, so what are you going to do next week, next month, next summer? And so I have really, great pleasure working with her. And it's just a couple of days ago, last week I should say, I told her that my plan for the summer is to come back to the research after I, get back from China. So I'm leaving for China next week. So Wednesday I give a final to the whole class of people who are taking physics of semiconductors. And so she wrote on the exam, have a nice trip. And I felt like, this person is really listening and caring. So for that, I give her like 10 extra points. So let's give Nicole one welcome.
Hi everyone, my name is Nicole Peyco, and I've been working with Dr. Shi on fabricating and characterizing zinc oxide thin films and doping them with magnesium and indium, which I'll explain. Okay, first off, thin films have many applications. There's microelectronics, which is for data storage. There's also water-resistant coatings. I read a couple articles that talk about mimicking shark skin on swimsuits. You can't compete in them. It's banned, like in 2011, but they tried. There's also optical coatings for anti-reflectance coatings that we see on our windows, so that's kind of like what we see every day. And there's also biological implants where they use polymer thin films to really maintain, restore, and hopefully improve damaged tissue that was damaged due to certain diseases, as well as solar cells, sensors, and more. So there's many applications. So really, let me just talk about what a thin film is. And so here's just kind of a picture so you can kind of get an image of what a thin film kind of looks like. So first off, you have a substrate. In my case, it'll be glass, which I'll show you in a little bit. And then you have like these orange particles, and that's just when you layer a thin material, which is about a fraction of a nanometer, 2 micrometers thick. So it's very small, so this is not to scale at all. But so as you continue it, you just kind of stack them on top of each other, and that's how you form thin films. So the purpose of my project is to make a transparent and conducting thin film using zinc oxide, and the reason why we're using zinc oxide is because it's known for its absorbance in the UV light. Just like your sunscreen, it just has zinc oxide in powder form, so hopefully the sunscreen absorbs the UV light instead of your skin. And so I'm using the spin coating method, which is a simpler process than what is currently used today, which I'll talk about later. It's called sputter deposition. And I will be using indium as a dopant, so we are running out of indium. It's a very scarce material, so we have to use it more efficiently. And we use it because it's known for its conductivity, high absorption, and transmittance as well. So first off, let me talk to you about how solar panels are currently made. So right now they use indium tin oxide, also known as ITO, and it's known for its high absorbance as well as conductivity on the surface, and so that's why they really use it. But in this case, their main component is indium versus mine, where it's zinc oxide. So here they have the sputter deposition technique, and this is just kind of an image of the inside of the machine and what it looks like. So essentially what is happening is that there's these gas ions that are accelerated by applying voltage, which produces this plasma right there in the yellow. And then they're bombarded, the atoms on the target, also known as the cathode, they bombard the atoms and eject them, and they move across the chamber to deposit onto the substrate right here. So an advantage of using this is that you can really measure the thickness and control the deposition rates. So that's a really good thing to have. But the disadvantages are it's costly to maintain. The scale process is fairly difficult and expensive, and it needs a vacuum, so it's just more expensive. So the experimental methods that we thought we should try is using zinc oxide as a solution. So what we have is zinc acetate and then MEA and DEA. And so the MEA and DA really are a sticky solution, so if you were to feel it, it's kind of thick and sticky. And so that just really helps us bind our zinc oxide to the substrate, which is here in the glass. And so I use dopants, and dopants are just when you add very low concentrations of different materials to really check how it changes the structure. So here I have my zinc oxide doped with indium. So as you can see, it kind of has this yellowish tint to it, but it's fairly transparent. And I also use magnesium acetate, and we use that because it's known to widen the band gap. So what a band gap is that you have the valence band and the conduction band, and that's the space between is how much energy it takes the electron to move from one band to the next. So it has a wider band gap, so it's harder for these electrons to move up, but it can also handle higher voltages, which will benefit us way later on. And then indium chloride helps reduce the band gap, which is what we're hoping for at least, and that makes it easier for the electrons to move from one band to the next, so we can have a conductive material. And so that's my doping process. I just kind of add various concentrations of magnesium or indium at a time and really just check how it changes the structure of my zinc oxide. And so here I have the spin coater, which right there is like the silver wafer, and that's where I put my glass substrate, which I'll show you in a video fairly shortly. Thank you. And so here we have, that's my solution, and it's being mixed and heated because we find that it helps actually glue it essentially to the glass a lot more efficiently than when it's cold. And so here you have, then I place the glass on the silver wafer, and there's a little hole so it kind of sucks it in and holds it in place. And then I press the pump, and it spins about 2,000 RPM. And then I just kind of get a pipette, it's plastic, and I just dope it. So it's a fairly simple process. And you can see the little drops. And so what we're hoping is that it's uniformly coating the sample as it's rotating. So those are just the first couple steps. After I coat my sample, I anneal it. And annealing is when we put it in a furnace and essentially bake the sample onto the glass. So it really sticks on. And so here is the furnace. Ours goes about to 1800 degrees Celsius, but I use it anywhere from 150 to 400 degrees Celsius. So after I do that with various times and temperatures, I check it in the UV vis, also known as the ultraviolet visible spectroscopy. And this is the one I use. So it's fairly small. And most of those you see them with cuvettes with liquids in them, but since mine's a solid, we have our own, and so it just kind of has a hole in it, so I can just have the sample be on it and the lights can still shine through. So essentially what is happening in the machine is that you have this source light, and it's shining through essentially through a prism. It bends, the light bends at different wavelengths, and then it goes through the sample, and the detector detects how the interaction between the glass and the different wavelengths of the light really interact. And so through that process, I get my data. So this is the data that I use for zinc oxide doped with magnesium. And first we get our transmittance data. And that's just to check the transparency. And that's a big part of this project because we want it to be at least 70% transparent or higher. And that's just for quality because we want the photons to be able to really go through. And so the blue line is the zinc oxide. And we can see that it's at about 90% transparent, which is good. And then we have 15% of just the magnesium, which is this red line, which is about 75%. And then 30% was oddly a little higher, and that could be due to various annealing temperatures, because that dissolves some of the unwanted solvents, so we have more zinc oxide. So that could have been something that changed. And then about 50%, we get about 40% transparency, which is not desirable. It's not something we want, but that is what we got, and so we know that above 50% is a little too much for magnesium. And so also we check the absorbance, and that's a key component because we want the UV light to be absorbed, so anywhere from 250 to 400 nanometers scale on the light spectrum. And our zinc oxide gives us this nice little slope and fairly flat to zero after about 400, which is something that we're looking for. So that's just kind of our starting point. Then 15%, this red line, we can see it's slightly shifted in the absorbance, but it starts at the same and it has a general same slope. And then 30% has a nicer slope and actually goes to zero a lot faster, which is something that we also liked. And then 50%, once again, it was a little too much, so the quality of our line was not desirable. And so through all this information, we can calculate the band gap, and that's also another important component. And so zinc oxide tends to have a 3.33 electrovolts band gap, and experimentally, this black line, which is where I calculate the band gap, indicates that our zinc oxide had 3.32 electrovolts. So with magnesium, we expected it to shift and move to higher electrovolts, and that's what we were able to see. So the red one represents the 15%, and we got about 3.37 electrovolts. And then 30% magnesium, we got 3.57, and then 50% we got 3.61 electrovolts. And then after about 50%, the highest I could really get it to is about 3.7 electrovolts, but also the quality went down, so I focused mainly on 15 and 30. So then separately, I doped my samples with indium, and that was really to just kind of get a conductive thin film. So this one was a little bit of a different process. We stuck to one concentration, which was 3%, which we read from other articles that said 3% is good for conducting. So here we have this red line. So before, I would layer about 25 coats, so it took many hours. But we did it, and we did it at 150 degrees Celsius, and we only annealed them for about 10 to 15 minutes. And so it was a short annealing just to kind of get some of the solvents just kind of stick to the glass a little more, and then as we continue layering it, more of the indium is on, and so we can have more, hopefully more conductance. So here, the blue line, after we annealed it for the big annealing, so that was really for an hour at 400 degrees Celsius, it really just helped bind the solution all together. So then we were able to get a resistance other than infinity, which I will show you soon. So this is a transparency, so you can also tell that the transparency of the red line is a lot nicer than the blue line, but we were able to see the change. And then here in the absorbance, we were also able to see this red line, and it went really straight down, which was really nice. And then once we annealed it for an hour, we were seeing a decrease in the absorbance and also a decrease in the slope. And then the band gaps finally. So zinc oxide in the previous slide we saw had about a 3.33 electrovolts for the band gap. And before annealing, we only got 3.30 electrovolts. And we think it's maybe because there's a lot of zinc oxide and we haven't really done this big annealing, so it wasn't really able to bind too much of the indium. And so after we annealed it, we got it up down to 3.0 electrovolts with a resistance of 1.9 mega ohms, which is still too high. We want it in the ohms or kilo ohms area, but we did get a final resistance on the surface and we got the band gap down. So we were really able to see that indium does shorten the band gap. And so really the conclusion of the project is that magnesium doped zinc oxide has shown to really blue shift, so widen the band gap compared to just zinc oxide, as well as indicating that magnesium doping has really modified the structure of zinc oxide, which is something that we got to see. As well as the indium dope samples had a red shift, so we got to get some conductivity on the surface, which was one of the main goals. And so the next steps for this project are to really just continue to lower the conductivity on the surface. So that can mean that we have to increase the percentage of indium, so we can go to like 5 or 6% and see how many layers we have to do, or we can just continue like maybe doing 30 coats of the thin film onto the surface. And so that will really just help us achieve this conductant transparent oxide for solar cells, because then we can even double dope the sample, so putting magnesium and indium all in one and seeing how the band gap is tuned with those circumstances. So I would like to thank Dr. Shi as my mentor. He really helped me through this project, even though I asked a lot of questions. I got to learn how to independently run a lab, which benefited me. And then I would like to thank the Hitchwas for funding me for the summer research, the Source Award for additional funding, as well as the SSU Office of Undergraduate Research.